Condensation polymers. Polymer is a name for a really, really long molecule made up of lots of short molecules called monomers. Let's have a look at a reaction that you may have seen before. If we take this molecule, a carboxylic acid, react it with an alcohol, remember R just represents a general group, an alkyl group, we form an ester on water. So carboxylic acid plus alcohol, they join together releasing a small molecule of water and an ester. Now if you look at the structures carefully, you can see why an ester is formed and why water is released. So if you take the OH of the carboxylic acid, join it to the H of the alcohol, it makes a water molecule, and then that carbon with the oxygen bonded to it joins to that oxygen, and that makes the ester link. So this is an esterification reaction. It's also a condensation reaction because two big molecules join, releasing a small molecule. But things start to get really interesting if we put two functional groups on each molecule. So for example, if we were to draw propan dioic acid, prop for 3 carbons, and dioic acid means there's 2 carboxylic acid groups on the same molecule, and then we react it with an alcohol that also has 2 alcohol groups on it. So let's have a look at ethan-1,2-diol. What reaction would happen now? Well, you've still got a carboxylic acid and an alcohol group that can react to release a water molecule. So the OH joins to the H, kick out the water, that carbon joins to that oxygen, and we can form an ester link in exactly the same way that we did before, releasing a water molecule. The only difference now is that at the end of the molecule we'll have an unreacted carboxylic acid on one side and an unreacted alcohol group on the other side. But in the same way as before, we'd release a water molecule. But what happens if we take this ester product and we react one of the ends with another molecule? So for example, let's take our ester and join one of the ends, the alcohol end, to another carboxylic acid molecule. So we'll pop the ester down here, get rid of the water. That was our product from before. Okay, so we've got our same product, the ester, and let's react it with another molecule of propan dioic acid and see what would happen. Again, there's no reason that this shouldn't form another ester bond. We've got an alcohol group, an OH group, and a carboxylic acid group. So if the OH group of the carboxylic acid joins to the hydrogen of the alcohol, and that carbon joins to that oxygen, we'll form another ester bond. And our molecule will just be a bit longer. So we start off from the left-hand side, we've still got that original carboxylic acid there, joined to the CH2, another C double bond OO, and then from the alcohol we have those 2 carbons in the middle, CH2, CH2. But we've added an extra ester bond in here, so it's O, C double bond O, CH2, and then we've got the unreacted carboxylic acid group at the end. And you can probably see that we're starting to form a pattern here. So if this bumps into another molecule of alcohol, either of those ends, the carboxylic acid ends, could react with the alcohol to lengthen the chain. And in fact, in our reacting system, we've got hundreds of thousands of billions of molecules kicking around. So in fact, with lots of options for this reaction to just keep going. So what we're doing here is we're forming a really long chain, which is linked by ester bonds. So the long chain is a polymer, and the polymers join together by ester bonds, so it would be a polyester. And that is literally the same as you've probably heard polyester when you're talking about clothing fabrics. This is how polyesters are formed. And we can draw a long section of our polymer chain, just keep the pattern going on and on and on like this. Carboxylic acid, alcohol, carboxylic acid, alcohol, so on. And every time they join together, a water molecule is kicked out. So it's actually called Condensation Polymerization. Condensation, remember, means as the molecules join, we release a small molecule of water. Now, it's hardly practical to draw the whole section of the polymer chain out every time we want to show it. So we're going to find something called the repeating unit, and you want to look at bits of the pattern that are the same. So you've got that OCH2CH2, then the OCH2CH2. If we draw a bracket before that oxygen on one side, we need to draw it before the oxygen on the other side, so we're not including it twice. And then that section would be called the repeating unit. In fact, you can make this reaction simpler in lots of different ways. So we can isolate the repeating unit and draw that, repeating over and over again. And we can simplify things down further. We can get rid of that middle bit and just draw it as a coloured box instead of writing the stuff that's in the middle. We can just simplify it down. And in fact, you could put any linkage, any number of carbons and hydrogens. You could even put benzene rings in the middle. So when we do draw these boxes, what we're doing is we're beginning to generalize. And in fact, generalization adds more information. It tells you that it could be a whole number of different things. And you could actually put the same boxes into your repeating ester chains. You can see where those things form. So although it seems like we're removing information by putting these boxes in a sense we're adding information because we're saying it could be any linking groups that would be there. So with this in mind, when we can find repeating units and when we can use generalizations like this, we can actually make the reaction a lot simpler. So let's have a look at how we would simplify this reaction now. And this is a common notation that's used to show polymerization reactions. So you take N, representing a very big number of dicarboxylic acids, and they're linked together by whatever we want to put in the middle. We'll just use a red box to show that. And it's dicarboxylic acid. It's got 2 carboxylic acid groups, taking the same large number of dialcohol molecules. And again, we can put anything we want into the middle. And they're going to form a condensation polymer. Now, the tricky bit is getting that repeating unit. So we're going to start with the oxygen that goes to the carbonyl group, put the red bit in the middle, another carbonyl group, then goes to another oxygen. And then you've got your blue box representing the bit between the 2 alcohol groups. And you've got to work out whether you put that final oxygen in. If we did, what we'd find is that you'd actually have a second oxygen before you get to the carbonyl. It wouldn't be right. You don't want to put the oxygen in twice. You've already got that oxygen in once. So in fact, we close the brackets there, pop an N in at the end of the brackets to show that that's a repeating pattern. And then we write 2NH2O. So in fact, for every repeating unit, 2 water molecules are released because we have 2 ester bonds per repeating unit. So that's like the general equation to show this reaction forming polyesters. But there is actually one other way that you could form a polyester. If you had a molecule that had a carboxylic acid group linked to an alcohol group in the same molecule, so it's not a diacid and a dialcohol, it's actually something with an acid and alcohol group in the same molecule, you'll also get a polymer. Now, to work out the repeating unit, we need to draw a section of the polymer chain. So you get C double bond O green box to the O that was joined to the alcohol, which will then be joined to another C double bond O of the next monomer with the green box, then the O of the alcohol, then that's joined to the C double bond O. So in fact, the repeating pattern's a little bit different here. It's O C double bond O green box, O C double bond O green box, O C double bond O green box, and so on. It's slightly different to the pattern that we had in the previous type of polyester. Again, the repeating unit can be shown as long as you don't repeat the same atoms in. So if we do it just before the carbonyl group on the left-hand side, and then we need to do it just before the carbonyl group on the right-hand side. So we're not including the same atom twice in the repeating structure. Then we pop an N by the brackets, and this time it's just N number of water molecules, because we've only got 1 monomer per repeating unit. So that's how you work out that it's just NH2O. So I hope this has been helpful to learn about the structure of polyesters.